The pulley shown has a radius of 12.96 centimeters. Suppose it takes 18 seconds for 56 centimeters of belt to go around the pulley. Find the linear speed of the belt in centimeters per second. Find the angular speed of the pulley in radians per second. So, yeah, what we're studying in this section is it's really focused on angular velocity and the specific application of angular velocity to like a uniform circular motion. And there's even further than that, it's only the case where the angular velocity is constant. So it's simplified cases so to illustrate the concept of angular velocity. But still, these problems are very interesting. And so, a lot of problems that you'll deal with in real life do involve circular motion. So you can imagine maybe an engine maybe the belt's driving this, or maybe an engine is driving, either this is being driven by the belt or this is driving the belt. And, this could be like a conveyor belt, right? This is attached to an engine. So with an engine, you can set what the angular velocity of the engine is going to be, or the motor, right? You can dial in the angular velocity, but how does that translate to the actual linear speed or the change in position per time, the actual speed of like the belt here? Again, they say linear speed. I don't like that term linear. They were just referring to like actual velocity, change in position per time, not change in angle per time, for example. Like actual speed, traditional velocity. That's what they're saying. That's what they mean by linear here. Okay, so what is the speed of the belt? What is it doesn't tell us the direction? Let's say it's rotating this way, like so the wheel's rotating this way, so the belt is going in that direction. What's the speed of the belt? Now you might say, isn't that a negative rotation in terms of angle? Yeah, technically yes, but don't get bogged down with that. We're just trying to solve this specific. We're trying to answer this question right in front of us. That's how problem solving works. But if there was a kind of a bigger question with a bunch of variables and all kinds of things going on, then you would want to use the traditional setup, the standard convention for positive angle and negative angle. Okay, if this could potentially be rotating in both directions, right? Like it could start in one direction, go in another, etc. Then you want to set up your coordinate system to where if there was a negative, we would want this to be this velocity would be negative because this angle would be going this way. And we want a negative velocity because we want to distinguish between positive and negative velocities, right? But this isn't that complicated. It's just a simple question here. So there's no need to bring in like negative velocities, right? Let's keep it simple. Okay, so the pulley radius is 12.96 centimeters, and it says it takes 18 seconds for 56 centimeters of belt to go around the pulley. So what is that telling us? Is that an angular? Does that allow us to get angular velocity? Well, no, because it's giving us a distance, not an angle, not like revolutions or radians. It's giving us a distance in a certain amount of time. So a distance in a certain amount of time, that's a traditional speed. That's a traditional velocity. So can we just take 56 and divide it by 18? Well, I mean, potentially, yes, but you have to be careful, analyze what they're saying to make sure that that's translating into what you expect it to be. So what is it saying? Let's read this carefully. It's saying it takes 18 seconds for 56 centimeters of belt to go around the pulley. So that's like the outer diameter of the circle here. It's telling us we're assuming the belt is not slipping. And with the teeth here, it's not slipping. So for every tiny distance, the outer diameter of the pulley moves, the belt moves with it. So like, in other words, the speed of the belt is going to be the speed of the outer diameter of the pulley. Okay. So if when the belt moves 56 centimeters, not in a line, but like it moves 56 centimeters of arc length distance. It does that in 18 seconds. So yes, we can just say we can say V, if we're analyzing this circle here as like the circular motion that we learned in this section. So there's an S, R, theta, omega, T. right? These are the variables that we can solve for when it comes to this rotating circle here. Well, we know that and v, and we know that v, the velocity, represents the speed of at the outer radius of the circle, or whatever circle we want. But we're thinking about this where the belt is. Okay, so yeah, the v here is definitely, it takes 18 seconds for the outer diameter here to move 56 centimeters. That's how fast the outer diameter is moving in terms of just traditional speed. So 56 divided by 18, 28 ninths. This is in centimeters per second. Okay, now, I put V here, and I shouldn't have done, well, no, that's right. Yeah, because the V of the belt, I was going to say that I didn't want to associate the speed of the belt with the speed of the circle here, the outer diameter, but that is what they are, the same. We just talked about that. So yeah, that's it. So V is equal, this V, the speed of the belt, is 28 ninths centimeters per second. But we could easily do a unit conversion on this to turn it into something more intuitive. Miles per hour, whatever, or maybe, what about feet per second? Okay, so 28 ninths is 3.11. So, you could just type in 3.11 centimeters per second, because how many feet per second, right? Google gives you the conversion easily, so 0.1 foot per second, maybe inches per second would be better. Well, usually okay, well, if it's that many feet per second, and there's 12 inches in 1 foot, then you multiply that by 12.102 times 12. So 1.2 inches per second. That's pretty intuitive, I would say. I think you can mentally picture that. Approximately 1.2 inches per second. So it's, it's moving pretty slow. If this was a conveyor belt, it's like, they're packing up something, so they don't want to go, they don't want it to move too fast. Okay, and just note, so 0.102 feet per second. How did I convert that to inches per second? It's easy. Feet per second, there's 12 inches in 1 foot. We're in inches per second. I just multiply 0.102 times 12. Okay, what is the angular speed of the pulley in radians per second? Okay, so it doesn't give us any information about the rotation here, but we have V. Let's see, we've got R is 12.96 centimeters. So with V and R, can we get to omega? So we know S is equal to R theta, omega is equal to theta divided by T, V is equal to S divided by T. Okay, S is R theta, theta divided by T is omega. Okay, yeah, omega is V divided by R. So let's see, let's get the units right. So 28 centimeters for every 9 seconds. That's another way you can read this. 28 ninths centimeters per second, or there's 28 centimeters moved in every 9 seconds. That's another way you can read that. Okay, times, we're dividing by the radius, so it's 12.96 centimeters, and then there's nothing up here. Centimeters cancel, and that's what we're going to get. What? No units per second, but no units, that's radians. Okay, so omega is 28 ninths divided by 12.24 radians per second. Okay, there we go. And similarly, you could convert this to an intuitive unit if you wanted to, like we did with inches per second. Well, it asks for actually, I shouldn't have boxed this in because the question asked for, it asks for this, 28/9 centimeters per second. So that's the answer to the question. These are the answers to the question, but in a real life situation, you could potentially put those units into something more intuitive. So to me, we would say, how many revolutions per second or per minute? So let's see, 2.24 radians per second, and you have one revolution. Well, no, okay. Actually, no, yeah, that was it. So one revolution for every 2 pi radians. Okay. Now we're going to make the number even smaller because we're going to divide 0.24 by 2 pi. So to scale it up a little bit, let's do this. There's 60 seconds in 1 minute. Okay, so now we're in RPMs. So that 0.24 times 60 divided by 2 divided by pi, 2.29 revolutions per minute, RPMs, yeah. So that's pretty intuitive. It's one revolution, or no, it's about 2.3 revolutions every minute.